Hi, I'm Mark Barsamian. In this video, I'll be discussing indefinite integrals where it's necessary to rewrite the integrand first before integrating. This material is from section 5.1 of the book, more specifically pages 326 to 330. Examples 2 and 3 are related to what I will be discussing, and this collection of 6 exercises from section 5.1. Let's start by recalling some things that we've discussed so far in Chapter 5. The definition of antiderivative, to say that a function capital F is an antiderivative of a function little f, means that little f is the derivative of capital F. That is, if you start with capital F and you find the derivative, you end up with little f. And then we've also discussed the idea that for a given function little f of x, there is a large collection of antiderivatives of little f. There's more than one antiderivative. Given a particular antiderivative called capital F, there's a whole collection of other functions that you can obtain by adding constants to capital F of x. And so this whole collection of functions, all of them qualify to be antiderivatives of little f of x. On this page, there's a typo. Let's recall our discussion of particular antiderivative and general antiderivative. The previous page, we were discussing the collection of antiderivatives of this function, little f of x equals x squared. And we discussed this one in previous videos, capital F of x equals x cubed over 3, and this one, capital G of x equals x cubed over 3 plus 17. Both of those antiderivatives of little f of x have an actual choice of a number c, whereas the whole collection of antiderivatives of this function were functions of this form, y equals x cubed over 3 plus c, where c has not been chosen. Well, these antiderivatives were a choice of a particular value of c has been made. Those kinds of antiderivatives are called particular antiderivatives. So we've got two of them there, that capital F of x and that capital G of x. But if a value has not been chosen for c, then this function form is called the general antiderivative of little f of x. And recall the definition of the indefinite integral. This symbol, spoken the indefinite integral of f of x, remember in that symbol, the function f of x that's sitting inside the symbol is called the integrand, and the frame around it is in two parts. There's this symbol there that looks like an S, sort of, and there's a dx, and they together form a frame around that function f of x. And what this symbol means, this whole thing means the general antiderivative of little f of x. And recall that the indefinite integral can be illustrated by these diagrams. If you have a function capital F of x whose derivative is little f of x, then we'd say that capital F of x is an antiderivative of little f of x. And then we know that the whole collection of antiderivatives of little f of x is denoted by this symbol. That is a function form. That is the general antiderivative of little f of x. And that is what is denoted by this new symbol, the indefinite integral of little f of x. And finally, recall the indefinite integral rules that we discussed in the previous video. They're presented here in this table, along with two new rules. The rules that we discussed in the previous video were these 5. The power rule for indefinite integrals is like the power rule for derivatives, going backwards, sort of, except there's one case when the rule does not apply. In the one case where that power rule does not apply, we have the 1 over x rule. The indefinite integral of 1 over x is not found by using the power rule, it's found by using this rule. The indefinite integral of 1 over x is ln of absolute value of x plus c. We've discussed the e to the x rule. The indefinite integral of e to the x is e to the x plus c. that one is fairly obvious, not surprising. But this ln of x rule sort of came out of nowhere. The indefinite integral of ln of x is this surprising expression, x ln of x minus x plus c. We, in the previous video, discussed the constant multiple rule. The idea is if you have an indefinite integral that involves a constant multiple times a function little f of x, that constant multiple can be pulled right through the indefinite integral symbol. That rule was fairly obvious. Another rule that's fairly obvious is one of the new ones for today, called the sum rule. If you have an indefinite integral involving little f of x plus or minus little g of x, that indefinite integral can be broken up into two separate ones. The indefinite integral of little f of x plus or minus the indefinite integral of little g of x. And then finally, these two rules, the sum rule and the constant multiple rule, can be put together into this combined sum and constant multiple rule. This rule says that you can do sort of the obvious thing. If you have an integrand of this form, a constant a times a function f of x, plus or minus a constant b times a function g of x, then that integral can be broken up into a sum or difference of two integrals, one involving f and one involving g, and in each of the integrals, those constant multiples get pulled through the integral sign. So again, the sum and constant multiple rule is sort of the obvious thing. Well, in today's video, as I said at the start, we'll be doing examples where the integrand needs to be rewritten, or all but one of these examples involves an integrand that needs to be rewritten. And we'll do that first before doing the integral. So we have 7 questions in this example 1, finding these 7 indefinite integrals. Here's the first one. Notice the integrand is of a form that does not fit any of our rules. None of our rules apply to an expression like that. So we have to start by rewriting the integrand. So there's the rewritten integrand. Now we can find the indefinite integral. So there you see a very long calculation. Notice the first rule that we used was the sum and constant multiple rule, which back in the days of taking derivatives was also the first rule that we usually used. And then we used the power rule, using n equals 1 to get this expression and using n equals 2 to get this expression. Notice that we have a combined constant of integration sitting out here. We get 1 plus c for both of these integrals combined. In the previous video, I discussed the issue of the constant of integration and how when you do each of these integrals, you get a constant of integration from each one of them. And those constants of integration would get multiplied by these constants, 51 and 17. But in the end, those constants can be combined into this single plus c. And then we simplified and we wrote a clear conclusion. Let's go on. Question B. The integral of 15 over square root of u du. Well, again, the theme for today is a lot of integrals where you need to first rewrite the integrand. Notice what we're rewriting the integrand into. We're rewriting it into power function form. I should have mentioned that in the previous example. We have a form that is power functions multiplied by constants and added together. All right, so now we've rewritten the integrand, we can find the integral. So there's our solution. Notice again, the first rule that I used was the constant multiple rule. Then I used the power rule for integrals with n equals -1/2. Now, from here on, everything is basically just simplifying. I had to be careful and simplify this -1/2 plus 1 that I got by using the power rule. -1/2 plus 1 is +1/2. I had to be careful. Dividing by 1/2 is the same as multiplying by 2. And then notice that this 15 gets distributed 2 places. I end up with a 15c. And here's one of those instances where I have an constant of integration, c, that can be any real number. So then 15c can be any real number. So I can just replace that with a new symbol that can represent any real number. Now really the hardest thing about this example was the rewriting. A lot of students are rusty with this kind of thing. The fact that square root of u is u to the 1/2, and the fact that dividing by u to the 1/2 is the same as multiplying by u to the -1/2. Let's go on. Question C. The integral of 1 over 5x to the 17th. Well, here's another one where, and this should be dx. Notice the previous example, the variable was u. I didn't have a dx, I had a du. Now we're back to having a dx. Well, here's a problem where I have to rewrite the integrand. We wrote 1 over 5x to the 17th as 1/5 times x to the -17. Now you might wonder why I don't just write that as x to the -17 over 5. It's because I want to write this as a constant times a power function. So this is, again, power function form. Now we're ready to integrate. So there's our result. A lot of steps there, starting with the constant multiple rule, then using the power rule with n equals -17, and then a whole bunch of simplifying, bunch of careful simplifying, being careful to note that -17 plus 1 is -16, so I end up with an exponent of -16 and a new denominator of -16. And then being very careful. An x to the -16 in the numerator is the same as having an x to the 16 in the denominator. So then the numerator just becomes the number 1. And then being careful to multiply 1/5 times this thing. I end up with a 5 in the denominator. And I've got to multiply 1/5 times c, and I get 1/5 c. But this is one of those constants of integration. C is a constant that can be any real number, so 1/5 c can be any real number. So we might as well replace it with a more convenient looking symbol. We just have a constant of integration now that's plus d. Let's go on. Question D is getting a little bit harder. Our integrand needs to be rewritten. We again have rewritten the integrand in power function form. Now we're ready to integrate. There's our solution. We started with the sum and constant multiple rule. We used the power rule twice, once with n equals 5 and once with n equals -5. And then we did a whole bunch of simplifying, being very careful to handle our exponents correctly. Notice that I don't try to do the exponent calculation in my head. I write down what the exponent calculation says that I'm going to do, 5 plus 1 or minus 5 plus 1. In the next step, I do that arithmetic. I get an exponent of 6 for that expression and an exponent of minus 4 for that expression. Common mistakes in this kind of problem is students will do this in their head and they'll end up saying that this will become x to the minus 6th because you raise the exponent by 1. We have to be very, very careful. What you're doing is you're adding 1 to the exponent. Minus 5 plus 1 is minus 4, not minus 6. Notice how different these expressions behave when you integrate. The left expression ends up becoming an x to the 6th, ends up with a higher exponent in the numerator. The other expression ends up with an x to the 4th in the denominator. So it looks like the exponent went down, but in fact, the exponent, as you can see, went from minus 5 to minus 4. So the exponent actually did go up. It just looks like the exponent went down because the expression is sitting in the denominator. And notice again at the end, I rewrote the final answer in not power function form. This should say positive exponent form. And the last thing I do is write a clear conclusion. Let's go on. Question E. Question E is the same format as question D. Two expressions side by side that involve fractions with x's in the numerator or denominator. But in question E, they're just a lot uglier. So we'll start by rewriting the integrand. Now we're ready to integrate. There's the solution, the same sequence of rules, the sum and constant multiple rule to begin with, and then the power rule, being careful of the exponents. Notice that dividing by 2/3 is the same as multiplying by 3/2. Similarly, dividing by 4/3 is the same as multiplying by 3/4. Notice a couple of other things. I'm very careful about writing fractions next to things that are not fractions. I have the fraction in parentheses, and I have the thing that's not a fraction written up on the baseline, not on the floor. And then notice at the end, I leave things in rational exponent form. I don't convert to radical form. I'm not a fan of this kind of radical form. The book presents some problems in that kind of radical form. But generally, rational exponent form is better. I don't mind the square root symbol for square roots, but for cube roots or other more complicated radicals, I'd rather just have fractional exponent form. Let's go on. In question F, we again have an integrand that needs to be rewritten. Now, notice that I did not go all the way and write this in power function form. This term, 1 over x, if written as a power function, would be x to the minus 1. Well, remember that the power rule for integrals does not apply to the case where the power function has an exponent of minus 1. If I want to integrate 1 over x, I need to use the 1 over x rule. So I want to leave my function as 1 over x. So this form, I don't want to simplify or rewrite any further. Now I'm ready to integrate. And there's our solution. Notice how differently these two expressions integrated. Integral of 1 over x ends up giving us ln of absolute value of x. The integral of x ends up giving us x squared over 2. So again, be on the lookout for 1 over x. You don't want to write that as x to the minus 1. You don't want to try the power rule for that function. That cannot be integrated using the power rule. You have to use the 1 over x rule. Let's go on. Question G might look at first like we don't need to rewrite the integrand, but in fact we do. I want to write this plus 5 as plus 5 times 1 so that I have a constant times a power function. Now we're ready to integrate. There's our solution. We started with the sum and constant multiple rule. Then we used the e to the x rule to find this integral. And to find the integral of 1, remember that 1 is a power function. 1 is the same as x to the 0. So we use the power rule with n equals 0. Now, remember, when you find the integral of this, there is no x in that integral. There's just you're integrating 1. But when you use the power rule, an x shows up here. You have to have an x to do the power rule. I mean, you put an x, you create an x out of nothing, and you create an exponent for it using this calculation. So even though there was no x in that integral, you end up with an x as a result of using the power rule. And that's the end of that example. Let's go on. In example 2, I want to consider valid and invalid solutions to an indefinite integral problem. So in this problem, one of these 5 solutions is correct. Each of the other solutions has at least one invalid step. The equal signs are all numbered, so our job is to discuss the validity or invalidity of each equal sign. Conclude by saying which solution is the correct one. Now this will be fairly tedious, but it's very productive to do this exercise. So let's just dive in. Let's look at solution A. We're going to go equal sign by equal sign through this solution. Now notice that in this solution, what they did in this first step is they rewrote the integrand. They didn't actually integrate. I prefer rewriting the integrand first before integrating, but that's okay. So, this is a style thing. Now let's look carefully at what happened in this step 1. This x to the 5th got moved from the denominator up to the numerator to put it in power function form. That's okay. It becomes x to the minus 5th in the numerator. But wait a second. That 7 got moved from the denominator up to the numerator. That's not allowed. So that equal sign is invalid. We can't do that. Can't bring the 7 up like that. What about the second equal sign? What happened in this next step? Well, in this next step, the power rule is used. So the new expression would be, instead of the integral involving x to the minus 5, we would end up with x to the minus 5 plus 1, which would be x to the minus 4, divided by minus 5 plus 1, which would be minus 4. So this equal sign is okay. What about the next equal sign? Well, in going from here to here, all that happened is one of the 2's got canceled. And so that equal sign is okay. And then what happened in this last step? Well, in this last step, this x to the minus 4 got taken down to the denominator, and that's perfectly okay. So this first solution is invalid because it contains an invalid step. Okay, let's go on to the second solution. In the first step, an x to the fifth got moved from the denominator up to the numerator, and it became an x to the minus fifth. And notice that that 7 stayed down in the bottom. So this first step is correct. The next step, what happened? The power rule was used, and that's okay. Now let's see what happens next. In the next step, the x to the minus 4 got taken down to the denominator where it becomes x to the fourth. That's okay, but look, that 2 got taken down to the denominator as well. That's not okay. Can't do that. So this equal sign is invalid. Now what about the final step? In the final step, all of these numbers, 7 times minus 4 times 2, got multiplied together to give us 56 with a minus sign out front. So that last equal sign is actually okay. So in this second string of equations, only that one equal sign in the middle is invalid, but that makes this solution invalid. Let's go on. Question C. Well, let's see. In the first step, the x to the fifth gets moved from the denominator to the numerator. It becomes x to the minus fifth. That's okay. In the second step, we use the power rule. That's okay. In the third step, the 2 gets canceled, and we end up with just a single 2 in the denominator and a minus sign out front. And so that third step is okay. And in the fourth step, the x to the minus 4 gets taken down to the denominator where it becomes an x to the fourth, and the 2 and the 7 get multiplied together to give us a 17. So the fourth step is okay as well. So this one is valid. Let's go on. Question D. In this first step, the x to the fifth gets taken up to the numerator to become x to the minus fifth. That's okay. But look, the 7 gets moved up as well. So that's invalid. Let's go on. In the next step, the power rule gets used, which is okay. In the next step, a 2 gets canceled, giving just a 2 in the denominator and a minus sign out front. So that step's okay. In the last step, the x to the minus 4 gets brought down to the denominator, becoming x to the fourth. But look, the 7 got moved down to the denominator as well. Can't do that. So this equal sign is invalid. The final equal sign is okay. The 2 and the 7 get multiplied together to give 14. But since there are 2 invalid steps, this solution is invalid. And finally, let's go on to the last one, question E. The x to the fifth gets moved up to become x to the minus fifth. Okay, that's okay. Notice the 7 stayed down at the denominator, so that's a good first step. And then look what happened here, though. When you integrate, the new exponent should be minus 5 plus 1, which would be minus 4. So that's an incorrect exponent. And the denominator should be minus 5 plus 1, which should be minus 4. So that's incorrect. And let's go on. In the next step, the 2 canceled that minus 6 to give us a 3 with a minus sign out front. So that third equal sign is actually okay. And in the final step, the 7 and the 3 multiplied together to give us 21. So that's okay. But this solution E is invalid because there's an invalid step. So notice that of all the solutions, only C is valid. All the other ones have an invalid step. But wait a second, look at solution D. Solution D came up with the right answer. Isn't that okay? Does it really matter that some mistakes were made along the way? Isn't this right because the answer is right? Well, no, if you think about it, look at all of those solutions. Solution D is the worst one. It has 2 mistakes. It has a mistake there and another mistake there. Happened to give the right answer, but this is a terrible solution. There are 2 mistakes made. This one is worse than A, B, and E. In those solutions, the answer was wrong, but at least only 1 mistake was made. So the moral is these integration problems involve very careful reading of all the symbols and being very careful with the arithmetic. And it's not just that the final answer needs to be correct, the steps along the way need to be valid. Now, in my posting of the notes for this, the things that we discussed about these various solutions are printed here in the pages that follow. The remarks about each of the steps in each of those solutions. So that's the end of that example, and that's the end of the video. Thank you.